All right, so let me introduce our next speaker, who is Pascal Faure, who is a professor at EPFL. So Pascal has a rich career, and one of the topics in your career, I think, was focused on specifically on physics modeling and computer vision, and combining these two. So in fact, when I was a master's student, Pascal's work was my golden standard. But since then, so Pascal has done much work, and his interests range from shape modeling, motion recovery, analysis of microscope images, and many others. Pascal is also a co-founder of several successful companies, Pix4D, Playful Vision, and Neural Concept. And I think he's going to talk about some of this experience in his talk, which is about deep surface meshes.
So Yvon did not tell me when he invited me that I had a role here, is to comfort all those depressed scientists who think that LLMs are going to put them out of business. So I'm here to say, no, there is hope. And Irfan in his talk said that data always wins. Yeah, I have to agree with that. But there is a saving grace. You don't always have the data. At which point you still have to do something. And that's what I really want to talk about today. And for this, I would first like to take you a few years back, a trip down memory lane. We are in 2001. We send our students to the top of Matterhorn. They launch a drone. The drone brings back a bunch of pictures, and we get a 3D map, an accurate 3D map of that part of Switzerland. So that technology is actually ancient. I mean, that goes all the way back to the 1960s. But it took about 50 years, so until 2011, to make it automated enough to make a company. There was no manual intervention anymore. You just got the pictures, computer did the rest. And there was no deep learning. Yay. And then we did things like this, where the Matterhorn doesn't deform very much, but this baseball that's being shot against a baseball bat deforms a lot, because it goes there very fast. And at the time, we were working with the Baseball Lab of America, the Wazoo in Washington State University. And these people are mechanical engineers. They are interested in the physical properties of the baseball. How does it deform? And they were developing simulation codes. And what we did was to provide the ground truth. So basically, here's the ball. Here is a model of the ball deformed to match the contour in the image, a 3D reconstruction, and a 3D reconstruction over time. And what that was used for was to essentially validate the simulation codes that those mechanical engineers were writing. Whatever they predicted should be what we actually observe. Okay, so these two examples essentially rely on traditional representation of surfaces as Euclidean meshes, which is, Euclidean meshes are great. They are used extensively for a good reason, but they also have a few drawbacks. One is their topology is fixed. It's really hard to change the shape of a deforming mesh, the topology of deforming mesh, and they are not terribly deep learning friendly. So at the time, it didn't matter. Now, of course, it does. So one representation that actually is better, not better, but really good in our brave new deep world is implicit surfaces, which, by the way, is another old idea. We all got, those of us who have gray hair, remember that we were all excited about this nice theorems in the 1990s. It was very cool, but it never took off. It's not it never took off. It didn't take off at the time for the reason I'm going to explain. So what is an implicit surface representation? It's, the idea is you represent your world in 2D or in 3D as a field function f, from either r squared or r cubed into r. And you design your function f so that it's positive outside, negative inside, and the surface is a zero crossing, the place where you go from negative to positive. The advantage of this, and why it was exciting, is because with this representation you can change the topology of your surface. You can create holes if you want, with everything remaining differentiable and smooth. So this is nice. But the problem was, how do you represent this function? So typically, I'm going to use for a lot SDF, sign distance function. The function is often taken to be the sign distance function, which means it's the Euclidean distance to the surface, but you make it positive on one side but negative on the other. And the problem was, how do you represent this function f? If you do it in a traditional way, you have to create a cube of data with values, and this is this is a memory hog. And if you want any kind of resolution, you explode. In 1990, you really exploded the memory of your computer. In 2020, you still do, in fact. So, problem, which is why it didn't catch on at the time. But then, deep learning happened, 2000, the fateful date of 2012 that I've seen on some slides. We changed paradigm, everything that had been done before becomes obsolete. Well, no, it doesn't. But you can do it better. And this is a beautiful example of that, which is these people that specifically, it's not me, it's these people, smart people, and they realized that, you don't need to represent the cube anymore. You can use a perceptron, a simple perceptron, to go from a point in space to the value of a sign distance function. And that is not that big. You don't need a huge amount of memory to do this. And in fact, you could even do a little bit better, which is you can condition the result on a latent vector or code that I'm calling C. So that for a given C, and for all x's, you are going to get different shapes. So you get a latent vector representation of shapes. For example, the shape of cars here in this example, the shape of cars. So how do you train this? Well, you have a database of shapes of interest, bunch of cars. You have your perceptron, and during training, you learn the weights, and you learn the vector C for each one of your examples at the same time. That's called an auto-decoding approach, and it works quite well. That's nice, and is very useful, but there's still a bit of a problem. And the problem is, let's say now you do need an explicit representation, for example, to do rendering, or as I'll talk about in a moment, to do computational fluid dynamics. What do you do? Well, you run the Marching Cube algorithm. That's the standard accepted way of doing it. It works, but it's not differentiable. It's slow, but more importantly, it's not differentiable. And that is a bit of a problem if you want to integrate that into a deep learning pipeline. You cannot have a non-differentiable operation. Okay, so that seems to be a problem, but in fact it isn't. And that's one of the things we've shown, that even though marching cubes is not differentiable, you can differentiate through it. So that sounds like a contradiction in terms, but it's not. So let's look at this a bit more carefully, and I'm going to do something that I haven't done much here today is I'm going to put equations on the board. One slide, only one slide. But equations are good. Don't forget them. So, let's say I have a loss function. And I have a Euclidean mesh that has vertices and facets. And I want to compute a loss, which is, for example, a rendering loss if I'm trying to model something. Okay, so when I compute this, how do I do? I have my S is my signed distance function. I run marching cubes, I get vertices and facets, and once I have V and F, I can compute L of V and F, no problem. The forward pass, in general, is not a problem. The place where you get into trouble with this is when you want to do the backward pass, when you want to differentiate. What you want to compute is the derivative of L, the loss, with respect to the code. So you do the chain rule for every vertex in your mesh. The derivative of L with respect to the position of a vertex, the derivative of a vertex with respect to the signed distance function, the derivative of a signed distance function with respect to the code. Okay, this one, no problem, because I'm assuming L is some differentiable loss function. This one, no problem, because S, I get S from C using a perceptron, I know how to differentiate that. Where I have a problem, or it seems like I have a problem, is this one. The derivative of V with respect to S, V is the result of the marching cube algorithm, which is a non-differentiable algorithm, so problem. But math is cool. That's the other message. Don't be depressed. Math is cool. There is something called the implicit function theorem. That says that because by construction, VI always satisfies the constraint, namely the value of the signed distance function at VI by construction is always 0, you can prove that the derivative exists, it can be computed, and in fact it's very simple. So even though the algorithm you use to do the actual computation is messy and complicated, you still can get a derivative, and that derivative here is the expression, it's dVds, so it's just a gradient of s, it's normal to the signed distance function divided by the square of the norm. By the way, if s is truly a signed distance function, the norm is 1, but the theorem remains true even if it's not a true signed distance function. So that's nice, because it means with this representation you can do things differentiably. So here's a small example. You start with a cow. That cow is defined by some code C. And I'm going to have a cloud of 3D points that has a different shape, it's the form of a duck, that's going to attract the shape. So how do I deform the cow into something else? I start with my C. I use marching cubes to compute vertices and facets. Once I have that, I can compute a loss and its derivative, and I can run a gradient-based algorithm. And here is the optimization where the little cow turns to a duck, and I chose this example because the topology changes. It went from genus 0 to genus 1, one hole. And it was smooth and differentiable all the way. So of course, I mean, ducks and cows are perhaps not something we're terribly interested in, but this has actually some very real applications. And one of them that we are working on, and Yvonne mentioned a startup, we have a startup that tries to do that, and the goal is to try to provide tools to optimize shapes, 3D shapes, to maximize their performance. In the case of a car, that means, among other things, minimizing the drag and maximizing the downforce. So it turns out that you can, you can train a GCNN, so a geodesic CNN, to take as input a 3D mesh, which represents the car, and output performance values. In this case, drag, and also local pressure values at every point on the car. So what I'm showing here is different cars, what you get by running a real simulator, which is accurate but slow, and what you get by running our trained GCNN, which is almost as good and a lot faster, and importantly, differentiable. Which means we can go from a code C to an SDF to a mesh to a drag value, and the whole thing, the whole chain now is differentiable, which means we can optimize. So we can minimize the drag of C with respect to C under a bunch of constraints, and the kind of constraints we want is, if this is to be a reasonable car, there should be some space for the engine and the passengers, for example. So here we are. We start with one of these big SUVs that we see in the streets of Dubai, and they are basically fuel hogs. And I'm not sure we can change that, actually, but we can at least make them more aerodynamic. And so, of course, this is just pure simulation, but we have a few examples of this working for real. So this is one of the earliest things we did, which was what you are looking here is the aeroshell of a reclining bike. So you can see the wheels here. And this is the finished product, where you have the shell, it's painted, you see the wheels, you see the two people who, the two bikers. And what they did was to go to this competition in Nevada, where they have an 8-kilometer long road, straight, flat, and they pedal as hard as they can, and they get clocked on the last 100 meters. And, well, they ended up going pretty fast. I mean, that's, I don't know. Do you imagine going 136 kilometers on a bike? Under only muscle power, of course. No electricity, no nothing. That's pretty impressive, and part of that success, so these were a couple of world records, the thing was low drag. And at the time, we were the first one to use that kind of technology. Now I'm sure other people are using it as well. And actually it's going to be interesting because after that there was COVID, so no more competitions for a few years. And we don't like this word here, men, student. We want world record, period. So they're going back this summer and we'll see what happens. And apparently, people in Switzerland seem to like world records. So this is another one that's even more ambitious. So we had various competitions of people building boats, electric boats, and trying to make them as fast as possible. And these competitions stopped for some reason, but the people who were working on them said, okay, well, what do we do now? And what we do now, what they do now, is they are going to beat the record, the world record, under sail this time. So, may not look like it, but this is a boat. It has 3 points, it's a tripod, and it's going to be pulled by a giant kite, and the design speed is 80 knots. For those of you who sail, that's insanely fast. And the current world record is 65. So it's crazy, but it's good kind of crazy. And And so here's the boat. They put it in the water for the first time at the end of last year. It's being pulled by a very small kite, so it's not going fast, but it gives you an idea of what it will eventually do, or what we hope it will eventually do. And again, so I'm coming back to the depressed scientist. If you work on this, you're not depressed, I can guarantee. And it's actually a very interesting problem for us to look at. I mean, there are many interesting problems, but in particular, this thing has a foil underneath that's designed to keep it into the water. It's being dragged by the kite. If you don't do anything, it's going to go flying, and that's not what you want in this case, so you need to create downforce to keep it underwater. And just to make things a little interesting, when you go at these kind of speeds, normal foils, so you know the beautiful America's Cup boats that we see on TV, they are limited at 50. They won't go faster than 50 because if you go beyond that, what happens is the foils start cavitating, which means they boil the water as they go through it, and they lose their lift, and it doesn't work. So you need to use these so-called super-ventilating foils, which exploits the cavitation process to create lift. And interestingly, that goes back, the profiles they're working on goes back to the profiles that were used in the 1950s. See, there's all stuff is somewhat still useful when they were flying hypersonic planes, the X-15. That's where they got the idea of how they are going to design these foils. But of course, we are not in the 1950s anymore. We now have these tools. We are going to use the mechanism I've described to actually optimize the shape of that foil to do what's supposed to do. So here I'm showing you the foil completely straight because it's a competition. I'm not allowed to show you what its real shape is, but the real shape actually has been optimized the way I'm describing it. So again, you could say, yeah, yachts, toys for the rich, who cares? But no, these tools are actually extremely useful in many, many industrial applications. So here in UAE, one that might be highly relevant is this one, where I've seen all these beautiful buildings that are being built, and one of the problems is that you want to position them in a way that the wind is channeled so as to cool the place and not to create windstorms. And there is a company, I mean, this is actually a slide here, I put the logo of the company because it's actually used for real for that purpose. And I've talked a lot about hydrodynamics or aerodynamics, but this is not the only thing. So heat exchange is completely amenable to this treatment. So there are lots of things like, I don't know, jet engines, for example, with heat exchangers, where you can optimize the shape to maximize heat transfer. And the math essentially is essentially the same. Okay, so that's cool, but after all, I am a computer vision researcher. I have to publish in CVP. I don't have to, but, well, actually, no, my students do, so yes, I have to. Publish in CVPR and similar venues. Let's do a bit of vision. This is applicable to vision, and in particular, in this case, 3D reconstruction from a single view, which, by the way, in my opinion, is a completely artificial problem, because if you want 3D reconstruction, you just get multiple views or zillions of views, and it works very, very well, but CVPR reviewer is kind of like single views or whatever. We'll do it. So you start with one image, and this time we train the network a bit differently. We try an autodecoder to produce our C codes. And so we go from an image to a code that recreates the chair more or less and then we optimize it. And eventually we get this thing here, which we have a 3D model of the chair from the single image. You can see it from the side. It's actually quite good. And it's not that easy because that particular chair has very, very narrow feet. And that's actually one of the cases where these SDF representations shine. They do this very well. And then you can even make it useful, fancy that, by using the same idea to go from sketches to 3D design. So you allow someone, an artist, to sketch something, and you will produce a chair or a car that corresponds to the sketch. And you can make it interactive. So you can, for example, take the result, say, well, I don't know, the wheelbase of that car is too wide, I want it narrower, why not? So you just sketch it a bit differently, and you have the thing that optimizes it on this basis. So I said it was useful because we've actually worked with neural concept to actually integrate that into a tool that you can give to designers. So in a car company, there are lots of engineers, great, but there is a very special population. And that population are the artists, the people who make the cars look good. And these people, I mean, why do you buy a car, an expensive car at least? Because it has higher performance? Nah, it's because it looks good. So these people are really, really, really important. And, but in general, they have not much expertise in aerodynamics. So with this, you have a tool that you can let them draw the car of their dream, something they know how to do very well, and the system will produce a real car that corresponds as well as possible to what they drew, and at the same time is aerodynamic. So that's machines. What we've also been working on is modeling people. And in this day and age, people wearing tight-fitting clothing can be captured very effectively using cameras. That's essentially a solved problem. What still is a little difficult is people, well, we tend to wear clothes. So modeling the clothes is still a bit of a problem. And we've adapted the techniques I've shown you to that. And there is one thing you have to change to make this work on garments is the fact that SDFs are very good for closed forms, closed, watertight surfaces. That's what they do. Well, clothes, by definition, are not watertight because you have to put them on. There are holes in them. So you cannot directly use SDF, or you can actually, by making a thick surface around your garment, but you lose accuracy. So an alternative to this is to replace the SDF by a UDF, an unsigned distance function, just the usual Euclidean distance. And if you represent that surface this way, where the surface is not what you have a zero crossing, is where the surface is zero, reaches zero. And the problem for us is that marching cubes is designed for SDFs. It doesn't work on UDFs because it expects the zero crossing that is not there. So what can you do? Well, you can actually modify it a little bit. And in the following fashion, if you have, say, a square or a cube in a voxel grid with unsigned distance values at every corner, what you're also going to have are gradients. And where the surface is, well, the gradients will face in opposite directions. So you can actually detect this by turning your UDF locally in an SDF by taking into account here whether gradients at neighboring corners agree or not. And you turn your SDF locally into a UDF, and you run marching cubes, and it actually works. So here's an example of the kind of things we can do when we model this shirt. You have the ground truth, you had what you get if you use an inflated SDF, which is a standard technique, and what you get with our approach, which is actually more accurate. And finally, one of the challenges of clothing is the fact that the clothing is not always tight-fitting. So one of the things we've been working on also is to add a motion model that allows the clothing to not follow the body exactly, if you want to model things like skirts in this case. Okay, so that's more or less where we are. Now let me tell you a little bit where we want to go. Again, we're not depressed, we're going places. And the cars I've shown you were actually one single surface. But that's not real, right? If you want to build that thing, a car has wheels, it has rear view mirrors, it has antennas, whatever. So you need to be able to build composite models of which the SDF is only a part. And so we've been doing this so that we can actually optimize all these parts together while forcing them to remain consistent. Here is the kind of optimization I've shown you. But now, if you look at a lot of the cars in various CVPR, ICCV papers, they usually have the wheels fused into the body. Well, such a car is not going to work very well. These ones don't. We explicitly use these more sophisticated latent vector representations to enforce the constraints and keep the wheels round and separate from the body. And this is based on this interpretation, which actually is a little clunky, but it uses three kinds of primitives. SDFs, the ones I've talked about, standard CAM primitives, and what we call CAD-driven SDF, which are SDFs that cannot be too far away from a CAD shape. And maybe to make this a bit more concrete, here is how you model a water mixer. Not terribly exciting, but it shows what it can do. So water mixer is this piece of machinery that you put two different liquids, you spin them, and when it comes out, they are well mixed. And what this model is doing, what you see happening here is we can change the latent vector so that the helix, which then SDF, changes shape, but at the same time, the cylinders that contain it and the bolts at the top and the bottom, they all remain consistent so that we can manipulate and optimize that thing. And while we're at it, we are not going to stop at pieces of machinery. Well, actually, of mechanical machinery. We can look at pieces of biological machinery, namely human organs. And the way we got into this is because we collaborate with a small company in Lausanne and the local university hospital that have built this beautiful thing, which is a surgery simulator. So the idea is if you need cardiac intervention these days, in general, it will be done endoscopically. You don't open the chest anymore, except in very rare cases. And you will, for example, insert the catheter. So this is this thing. The tip has an instrument that can, for example, burn when it needs to be burned or cut. And you insert it into the leg of the patient, so the artery that's here. You go all the way to the heart, and you do what you have to be done. And one of the problems with this is that, well, of course, it's difficult to do. And training a young surgeon to do this takes years. So the trainee typically will first just look, then they will be allowed to do very simple part of the process, and it's a long time before you go all the way where you let them just do it. And essentially the people in this company, who are all pilots, took a leaf out of pilot training. I mean, these days when you take a plane to go home, if the first officer on your aircraft is young, there's a good chance that pretty much this is one of the first time he's ever touched a real airplane. Most of the training will have been done in a simulator. Why? Because it's cheaper. And the same thing applies to surgery, or can apply to surgery. So they've built this surgery simulator where you insert the catheter here into the leg of the patient. It goes into the body of the patient, and the body of the patient is an empty box where there are cameras. And this time we have multiple cameras because it's an industrial product and we want it to work. The cameras observe what the catheter is doing because following the input of the surgeon, and then infers what it would be doing if it really were in the heart. Because it has a 3D heart model and it handles the collisions and everything that's to handle. And the result, we'll learn. The result is you have this, which is you see the catheter in the heart model that responds to your commands. And in this way, you can train your young surgeon, can train as much as he wants, he can kill as many patients as he wants, it doesn't matter, they're all virtual. And you can also, of course, plan an operation. One of the ideas here is if you have, a weirdly configured heart for some reason, we could build a model the night before. The surgeon can train on it or plan on it before doing the actual intervention. There is value to that. But of course, that means that we need to be able to construct good 3D heart models. And the heart, actually like the car, is made of several parts. There are 4 chambers in the heart, there are a number of arteries, and their connections are well known. I mean, this is a case where data always wins, yes, but a few centuries of medical knowledge isn't bad either. We do know quite a lot about the heart. So we can build a model that embodies that and enforces all these constraints. And furthermore, we don't only want a static model. We want a moving model because the heart is beating and killing the patient, so the heart is beating. So this is what we are working on, and essentially the kind of latent vector models I've talked about for the car, we're going to use exactly the same style for the heart. So to give you a little example, here is some basically what you get if you take an MRI, you run a segmentation. Your favorite is deep net segmentation. Segment any heart, I suppose, not as opposed to SAM. And you get a result which actually, so NNUnet is in the medical field is the one that's considered good. And you get something that's not bad, but not perfect. I mean, it does have these artifacts. And it's not the kind of thing you want to have in the model you're going to use to plan your operation. So you can try to fix it without imposing constraints or with imposing constraints. And that's actually what we're working on, which is you know that there are no interpenetrations. You know roughly how much, on what area these things are going to touch or not touch. So you can actually force your net to do that, and it gives significantly better results. So what we are working on right now is actually a more sophisticated version of the water mixer I showed earlier, which is a more uniform model that combines SDFs and primitives and allows us to add constraints in a reasonable way to do both, machines, hearts, you name it. Okay, so in conclusion, what I've shown is that we have a way in our models to combine explicit and implicit surface representations so that we can take advantage of their strength, their respective strength at any point of the computation. That the kind of function, implicit function we use, typically the SDF, is a very good one. But if you need to have open surfaces, you can also use the UDF. It works reasonably well. This approach can be expanded to complex composite shapes, and that's what we're working on these days. And I think it has potentially huge applications because most machines that we use, that we design, can be designed and optimized in this way. And actually, so I've talked about cars, I've talked about clothes, we could talk about heat transfer if you want to make things electric. And since I still have a few minutes, I'll mention this one, which is, we're going to save the world. Well, maybe not, but I don't know, a few years ago, DeepMind had this great paper where they showed they could control the fusion beam in the tokamak using reinforcement learning. Very cool. And they did it actually in the tokamak. So the tokamak is a research thing to do fusion research. They did it on the one that is on our campus, and several of the physics professors were part of this. And if you read the Nature paper, you'll see that in their discussion at the end, they say, well, there's a million things we could do to improve this, to scale this up. But one of them is to reshape the tokamak to make the control easier. So change the shape, the actual 3D shape of the vessel. And I could do that. Maybe not, but I would love to do that. Of course, a tokamak is worth billions of dollars, and if you make a mistake, you destroy everything. The chances that they will let me play with it are zero, which is why we work, on these boats where, okay, if you make a mistake, well, you make a mistake, right? But the hope really is that it will scale up eventually to these kind of super ambitious things. And maybe to conclude, you might have noticed I've not used the word LLM once. You can still do stuff without them. And on that, I will stop. Fine, no problem.
Okay, thank you, Pascal, for inspiring talk. Maybe I can ask the first question. So, yeah, this is really inspiring. I like it a lot. How do you answer these depressed researchers who want to animate avocado on riding horse on the moon? So right. How can they use your physics-based...
Well, it's actually it's excellent because we are collaborating with the Stanford people on this, on the horses. And a few things. I mean, not this specifically, but we've been talking about using occlusion boundaries to understand a problem when you take a horse or a person is, are you in this position or that position? There are ambiguities like that. And if you reason about the occlusion boundaries, you can solve it. So of course, we will use a foundation model and all that good stuff. But there is still room for putting on these kind of tricks that boost performance. And I think that's our role as academics. I'm not going to compete against Meta on making better models. I'm going to lose, I know.
Actually, if you want to animate on the moon, I guess with your model you can do the real gravity, moon gravity, so it will be...
You can do that.
Very good. Okay, more questions?
Yeah. Can I? Very impressive results on topological optimization and that things with bolts and everything. So my question is related to loss functions. Loss functions. Right. How you define loss functions? Because when you optimize, the question is the following. So it's a rare case if you have just a single loss function to optimize. Usually you face some hard and soft constraints. So maybe you need to do multi-criterion optimization. Probably my students should be watching now. You're talking online. So we discovered one thing on 3D reconstruction is latent variable systems and specifically photometric loss versus metric L1 loss, for example. If you train separately, results are like contradicting each other, and you need to mix.
Okay, so two things. One thing I'm pushing for and we're working on is hard constraints. Yeah. So if you know that, I don't know, the ankle has to be 90 degrees, make it 90 degrees, don't use a loss function. Yeah. So that because, and then once you've done that, you still have, so let's take the case of the car. You want minimize drag, you want to maximize downforce, you don't want your car to break, so there are some structural things, and the answer is Pareto optima. So you have a front of possible outcomes, and there is still a role for the engineer to say, okay, I want to be here on the front. So like this is, yeah. I mean, basically this is relatively standard engineering stuff. It's not easy, but the tools exist.
Okay, so and the second question is like how you basically decide if you do 3D reconstruction, for example, on modeling, and you need to find like a trade-off between like nicely looking, like Gaussian splitting, for example, on nerves, and you have photometric, but then you need to be like metrically consistent.
Right. Okay, so now we get into a problem I've seen many times, and actually, if anybody knows how to solve it, I'm interested. Is the ground truth is never the ground truth. So we've done a lot of modeling of blood vessels and neural structures and sort of things. And we do get ground truths, but the so-called ground truth is full of errors. Not because the annotators are lazy, because it's actually hard to do. And so we run our algorithm, we get a result that we believe to be better than the ground truth because we fixed the errors. But then in terms of the scores that we report in our favorite conferences, they're worse. And I don't have a very good solution for that. Now, for the kind of problems I've talked about, I mean, when I talk about drag or lift-to-drag ratios, these are well understood losses in the engineering world. And when you talk to a plane designer, he's going to say, I want these, he's going to go to give you specs, and you have to manage to be in those specs.
Yeah, thank you.
One more short question. Ali. Someone with microphone?
There is.
Please. Yeah.
Raise your hand.
Okay, thank you for the inspiring talk. Actually, my first question is regarding, like, most of the experiments we saw, or the systems are working on a single force or distributed force. So how...
On a single what, I'm sorry?
Like force or distributed, yeah. So what's the case when we have multiple forces affecting on the system?
Yeah, that was exactly the question I answered. Then you will have to find a Pareto optimum for your, so you want, I don't know, the obvious thing for a wing, say, you want to maximize the lift-to-drag ratio, but you want to maximize also the structural strengths because you don't want your wing or my foil to break. And these are different kinds of physics. But both of them are expressed by a loss. And I can either minimize for a weighted average of the two, which is what people tend to do, not very elegant, or actually explore the whole potential compromises you can look at and then there's still, as I said, there's still a role for the human designer to pick where on that Pareto front he wants to be.
Okay, thank you. And for just a small question regarding the 3D modeling for the heart, like the results you showed, does it use 3D unit or 2D unit?
It's so what the one I presented was NN unit,
Yes.
so it's 3D.
It's 3D.
I think the best unit these days are the ones that have annotation layers around the bottleneck. So I can actually like those. Actually, I am again. I'm a little bit leery of transformers. I'm really very old-fashioned, but I don't like the idea that you take your image and you break it into squares. That rubs me the wrong way. It works, I know, but it rubs me the wrong way. The unit with an annotation layer in the middle kind of gets around that, so I like them.
Okay, thank you.
All right, so let's thank Pascal again. So we are going to have a short break now, 20 minutes.